Hi everyone, my name is Sasha and I'm a customer engineer for almost 5 years at Google. I'm based in Munich and I'm here to talk to you about getting started with Apache Beam. So why is Apache Beam interesting? Well, for one thing, it's an incredibly powerful and flexible tool that lets you build simple ETL processes up to complex machine learning workflows. Another great thing about Beam is its unified programming model, which makes it easy to write code that can be run on various different data processing frameworks. In this presentation, I'm going to give you an overview of Apache Beam, show you how to get started in building efficient and scalable data pipelines. So whether you're a junior developer who is new to data processing or a seasoned pro who is looking for new ways to process data, I encourage you to stick around and learn more about Apache Beam. As I already said, Apache Beam provides a unified programming model for large-scale data processing. It offers a set of language-specific SDK for defining and executing data processing pipelines. As mentioned, it runs on various data processing frameworks such as Apache Spark, Apache Flink, Google Cloud Dataflow. So you are able to choose the right runner for your specific needs, such as performance or cost, for instance. Two of the key benefits of Beam are its scalability, which lets you parallelize data processing tasks on multiple servers. And on the other hand, it's the flexibility aspect where you can leverage built-in transformations, or you can define your own transformations based on your needs. To summarize that, Beam, as I said, provides one programming model, which lets you run multiple modes of data. On the one hand side, we are talking about bounded data, which is processed via batch, or we are talking about unbounded data, which is processed via streaming. So batch data sources can be a file, for instance, a database, and streaming services can be messaging services, for instance. Currently, Beam offers 3 SDKs in Golang, Python, and Java, and it runs on multiple runners such as Google Cloud Dataflow, Apache Spark, Flink, Apache Apex, or for local development, it also offers the direct runner, which whenever you're developing on your workstation, you can use to test or debug your data processing pipeline. So whenever we talk about Apache Beam, we often talk about data pipelines. And a data pipeline is represented as a graph of steps that are connected to each other. The data flows through the pipeline from one step to the next one, being transformed along the way. Each of the steps within the pipeline is a self-contained unit of work that takes one or multiple inputs and produces one or multiple outputs. Those transformations can, as I said, be either used the built-in transformations whenever we are talking about filtering data, mapping data, or grouping the data, or you can define your own whenever you develop a pipeline because you have certain business rules or business requirements that have to be applied on the data. The data itself in the Beam pipeline is represented as P collections, which is a collection of data elements that can be either bounded or unbounded. Bounded P collections have a finite size, meaning we know the size in advance. Whenever we want to process a file, we know how big the file is, for instance. And with unbounded sources, we have an infinite size because we don't know how many messages are coming in the future. The benefits of P collections are that they are immutable. So once they are created, they cannot be changed, which helps you whenever transformations are done on the P collection to minimize the risk of data races. They are also type safe. So whenever you create a P collection, you have to define the type, and just elements of that type can be added to the P collection. And whenever it comes to the portability aspect and running on multiple runners, each of them knows how to deal with a P collection whenever a Beam pipeline is submitted. So there is no need to change the data structure if you decide to move from one runner to the next one. In terms of reading data, we are talking about sources in Beam pipelines. They are used to read data from external data sources such as files, databases, or streaming services. There are a number of built-in data sources, but you can also define your own data sources as well. In a pipeline, we will see that afterwards. You have to create a so-called reader, which is then responsible for reading the data from the source and to produce the elements that are then processed in the data pipeline. On the other hand, when we are talking about the output of a data pipeline, we are talking about sinks. They are used to write data from a Beam pipeline to an external source. So again, they come in two flavors. On the one hand side, you have the bounded sinks that write a finite amount of data into a destination, can be like in a file in a database, and you have the unbounded sinks which write an infinite amount of data somewhere else. Again, also here, whenever you want to write data to an external system, you have to create a writer within Beam, and that writer takes then care of writing the data wherever your destination may be. There are I/O connectors. So I/O connectors are can be sources and sinks. There are pre-built I/O connectors out there that provide a unified API for reading and writing to a variety of data sources. They are listed on the Beam website. So if you want, you can have a look at what I/O connectors are out there. But if you have a certain specific need for an I/O connector, you can also define your own connector and leverage it in a pipeline. When it comes to transformations within a data processing pipeline, so you want to manipulate the data, you want to aggregate data, we are talking about an abstraction called P transforms, and several types of transformations are offered within Beam. Today, we will focus on 3 of them, starting with the element-wise transforms. We are then talking about the aggregation transforms, and then we will head over to the composite transforms. There, as said, there are a few more, but we will just focus on them as of right now. Starting with the element-wise transform, which applies a function to each of the elements in a P collection. So it makes it, especially for data processing tasks, a powerful tool, especially when it comes to cleaning the data, for instance, if you want to enrich the data, filter the data, or aggregate the data. They are quite simple to read as they are applied to any element in the P collection, so they are easy to understand. And on the other hand, they add performance, especially as you are applying them to every element of the P collection. The work can be parallelized and then split up across multiple servers. So It doesn't require just one server. The jobs can run parallel. In the example here, where we have 4 words as an input into the element-wise transform Pardue, and we want to key by the first letter. So we want to create the key value pair for each of the words. We will then end up with a key value pair which has the key S for storm, F for Flink, another key value pair with the key A for Apex, and the last one is again an S for key and Spark as value. They can produce element-wise transforms, can produce 0, 1, or many values for each of the input elements. In the example on the left, for instance, you see that we produce more outputs than we had inputs, where we start by substringing the first letter, then the second, the first two, the third, fourth, and so on of each word we have as an input, which is then a bigger output as we had in the input. And on the other hand side, they can produce less output than they had as an input, where we have, again, those 4 words as an input. And we just want to filter for words that are not starting, that don't contain an S. So we will end up with Flink and Spark as an output, and we are getting rid of Storm and Spark in this example. There is a list of predefined element-wise transforms where you have Pardue's filter, you have map elements and flat map elements, and then element-wise transforms for key value pairs, where you have just, for instance, just a value as an input, and you want to have a key value pair as an output. Or you have a key value pair as an input, and with just a keyword, the keys word, you can receive just the keys as an output, and the other way around, where you just have the values as an output. The next transform type we want to have a look at are aggregation transforms, which in more detail, they are a type of P-transforms that combines multiple elements in a P collection into a single value. So as an example, if you want to count the number of elements that are in a data set, or you want to calculate sum, mean, median, or any other statistical measure of a data set, they can be used for that. Another type of aggregation transform is the group by key, where you have key value pairs as an input, and you want to group all the values together that have the same key. Here in the example, you have the 4 words again, with the first letter of them being the key and the words the value. And if you apply a group by key, you end up with key value pairs that have, the first one has an S as a key that holds Storm and Spark. You have the next one where Flink is the value and F is the key, and the last one has an AS key and Apex as value. Another type of aggregation transform is the combined per key transform, which is a type of aggregation that applies a combine function to elements with the same key, which ends up where you end up with a result that is smaller than the actual input. In that example here on the slide, you see that you again have key value pairs, but instead of letter and word, we have this time letter and a number. And in that case, we have a key value pair that has S as a key and 6 as a value, F with the value 3, A with 5, and S with 7. And if we apply a combine per key and the sum, so we want to create the sum of each each key, we end up with 3 key value pairs, where S has the number 13, F has the number 3, and A has the number 5 as a value. And the last type of transform we are going to have a look at is the so-called composite transform. Composite transforms are a higher level of p-transforms that are built upon other transforms. So whenever it comes to certain data processing logic that has to be applied on multiple occasions within the code, within a pipeline, for instance, you can define a composite transform that contains various other transformations, and you just apply it instead of having to write the whole transform tree again. So it's just one transform that you have to apply. They are quite a powerful tool and enable you, as I said, for code reusability and a modular data processing logic. To close off the presentation, I want to show you a demo where we are now visually walking through it, and then we will see the code afterwards. In the demo, we are trying, so we are a fashion company, for instance, and we want to know what our most popular products are that are currently sold. And our challenge is that the data is currently in 2 storage systems, and the data can be small, the data can be big. And basically our aim and our goal is to create a data processing pipeline that actually finds the most popular product. So the data pipeline would look like the following. We have 2 data sources, the in-store data and the online data. So we have to connect to wherever the data is and have to get all the elements of the data. Our goal is then to extract the item IDs, because we want to know what the products are. And ideally, if we know the quantities that have been sold, we are extracting them here as well. We are then flattening the data, and we are creating a unified view of both systems. So all the data is then in one place. We create the sum so that we know how many times a certain item has been sold. And then we are using the top function, for instance, to show us the most sold products. And lastly, we could also store the results into any sink. In that case, for instance, we can write the results to BigQuery. I want to now show you a demo of how the visual graph here can be developed and written as code. So moving over here, our data sources in that case are 2 CSV files. One holds the offline sales and one holds the online sales numbers. And the data format is as follows. We have the order ID, we have a product ID, a product name, price, and the quantity that was sold of the item in a certain order. Similar, we have it for the online sales, and it doesn't necessarily have to be a file. You can use, for instance, 2 database systems. One holds online sales, the other one holds the offline sales. So you could combine data from various sources in that case. And the code looks like the following. I decided to use Python here. Starting, we have to import Beam, and we are then defining the names of the input files, offline CSV for the offline data and online CSV for the online data. And whenever we start developing the Beam pipeline, the first step is to create the pipeline, which is done here, where we call Beam.pipeline. And we are then able to add the different transformations. The first one is to tell Beam we want to read from a file, adding the file name and then also a parameter that says there is a header line in the file, so that should be skipped. And the next step is then to extract the relevant information that we need. In our case, the input here is the line itself, and we split it by comma. And we are then extracting product ID and quantity, and we return it as a key value pair at the end. So we have product ID and quantity sold in a certain order. Once we know all the elements and we have the product ID and the quantity as key value pairs, we can then create the unified view by flattening the data, and we are then able to create the sum. We do that by combining per key. So the product ID is the key, we combine them and sum the values together. We are then doing a transformation that we add the quantity that was sold of a certain product as a key and the name as value into a key value pair, and we are then selecting the products that have been sold the most. And the last step is to lock the elements on the console. Once the pipeline is defined, we can then run the pipeline. So let me just do that. By running it locally, we get the result that the product that was sold the most was sold to 1,385 times, and the second most sold product was sold 1,369 times. And we get 3 others since we told Beam to give us the 5 largest elements. I hope that gave you an overview of how Apache Beam works and how you can write your own pipelines. And I hope you're enjoying the rest of Beam College.